Two machines left Earth decades ago. They're still traveling, they're still sending messages home. Most space missions crash or burn out. These two kept going. Tonight we're discovering how these metal explorers broke every distance record, and how they're teaching us about the space between stars. Before we dive into this incredible escape story, drop a comment about where you're listening from. If you enjoy these cosmic adventures, consider subscribing. These stories of human achievement are meant to be shared. Right now, something amazing is happening in deep space. Two spacecraft are working perfectly in a place no human machine has ever been. The place where our sun's protective bubble runs out. Scientists call this region interstellar space. That's the empty zone between different star systems. One of our spacecraft crossed into this alien territory over a decade ago. The other followed shortly after. Think about the distance involved here. When Mission Control sends a radio message to these machines, it takes an entire day to get there. That's how far they've traveled from home. They're operating completely on their own in the cosmic wilderness. These machines were designed to work for just 4 years. They've been running for almost 50 years instead. Their nuclear batteries are still generating power. Their antennas are still pointing back toward Earth. Humanity's first ambassadors to interstellar space refuse to quit. In the late 1970s, the planets lined up in a special way. Jupiter, Saturn, Uranus, and Neptune all moved into perfect positions. This alignment happens once every couple centuries. NASA engineers realized something incredible. They could use each planet's gravity like a cosmic slingshot. A spacecraft could fly past one planet, get accelerated by its gravity, then rocket toward the next planet even faster. This technique is called gravity assist. The timing had to be absolutely perfect. Miss the launch window, and the opportunity disappears for generations. Mission planners designed what they called the Grand Tour. One mission could visit all 4 giant planets in sequence. No massive fuel tanks required. 2 identical spacecraft launched within weeks of each other. Voyager 2 took the long route to visit every planet. Voyager 1 took a shortcut to reach the edge of our solar system first. This rare planetary dance turned separate missions into humanity's greatest voyage of discovery. These spacecraft completely changed what we know about planets. They found active volcanoes spewing material hundreds of miles into space. They discovered underground oceans that might harbor life. They revealed that planetary rings are incredibly complex structures. Jupiter's moon shocked everyone. Scientists expected a dead, frozen rock. Instead, they found the most volcanically active world in our solar system. Sulfur eruptions constantly repaint its surface in brilliant yellows and reds. Saturn's moon Titan amazed researchers even more. This world has thick clouds and weather systems. It has lakes and rivers made of liquid methane instead of water. It's like a frozen version of early Earth. The spacecraft also discovered dozens of new moons around the giant planets. They found that Saturn's rings contain thousands of individual ringlets. Each discovery forced scientists to rewrite textbooks. These machines revealed that our solar system is far stranger and more dynamic than anyone imagined. Each Voyager carries a special cargo, a golden record containing sounds and images from Earth. Scientists designed these records to last billions of years in space. They're humanity's message to any aliens who might find them. The records contain greetings in dozens of languages. They have sounds of wind, rain, and ocean waves. They include music from Bach to Chuck Berry to traditional songs from around the world. They even have recordings of human heartbeats and laughter. The scientists also included detailed instructions for playing the record. They used universal symbols based on hydrogen atoms and pulsar stars. Any intelligent civilization should be able to figure out the playback system. On the record covers, diagrams show exactly where Earth is located in our galaxy. They use 14 pulsars as cosmic lighthouses to triangulate our solar system's position. These golden records are humanity's first attempt to introduce ourselves to the cosmos. In 2012, something unprecedented happened. Voyager 1's instruments detected a sudden change in its environment. The solar wind that had been pushing against the spacecraft for decades just stopped. The cosmic radiation around the probe completely changed. Scientists realized the spacecraft had crossed the heliopause. That's the boundary where our sun's influence ends and true interstellar space begins. Voyager 1 became humanity's first artificial object to cross into interstellar space. The crossing revealed that this boundary isn't a simple wall. It's more like a turbulent shoreline where two different oceans meet. Our sun creates a bubble of hot, fast-moving particles. Outside this bubble, the space between stars has completely different conditions. Voyager 2 crossed the same boundary 6 years later at a different location. The two spacecraft discovered that our solar system's edge is not perfectly round. It's more like a dented sphere being squeezed by interstellar forces. These machines are now swimming in an alien ocean that no Earth-based telescope can study. Interstellar space turned out to be nothing like scientists expected. The region between star systems isn't empty. It's filled with gas, dust, and high-energy particles racing through the cosmic void. The Voyagers detected something called the local interstellar cloud. That's a region of slightly denser material that our entire solar system is currently moving through. This cloud affects how cosmic radiation reaches Earth and other planets. The spacecraft also measured the true density of interstellar space. Even in this empty region, every cubic centimeter contains several atoms. That might not sound like much, but it's enough to create drag on anything moving through it. Most surprisingly, the magnetic field in interstellar space is much stronger than predicted. This field helps protect our galaxy from radiation coming from other galaxies. The Voyagers are now direct sensors in this galactic magnetic environment, sending back data that no Earth-based instrument could ever collect. Every day, these distant spacecraft face an impossible challenge. They must aim their antennas with perfect precision toward a moving target billions of miles away. Earth appears as just a tiny dot from their perspective. The radio signals they send are incredibly weak. By the time these signals reach Earth, they're fainter than a cell phone would be if you tried to detect it from another galaxy. NASA's most sensitive antennas strain to hear these whispers from the cosmic deep. The spacecraft are slowly running out of power. Their nuclear batteries lose a little strength each year. Mission controllers have been gradually shutting down non-essential systems to conserve energy. They're choosing which instruments to keep running as the power budget shrinks. Despite these challenges, both Voyagers continue sending scientific data. They're programmed to keep operating until their power finally runs out completely. Engineers estimate this will happen sometime in the mid-2020s. Until then, these mechanical explorers will keep reporting from humanity's most distant outpost. When their power finally dies, the Voyager spacecraft will become something extraordinary. They'll transform into humanity's first permanent ambassadors to the galaxy. These silent messengers will drift through space long after human civilization ends. The spacecraft are now on trajectories that will carry them past other star systems. In about 40,000 years, Voyager 1 will pass within a few light years of a star called Gliese 445. Voyager 2 will encounter different stars on its own path through the galaxy. Their golden records will outlast every human monument on Earth. While our planet faces asteroid impacts, ice ages, and the eventual death of our sun, these metal time capsules will sail on undisturbed. They're designed to survive for billions of years in the vacuum of space. Perhaps someday, an alien civilization will intercept one of these spacecraft. They'll find our golden record and decode our message. They'll learn that once, on a small blue planet orbiting an ordinary star, a curious species built machines that could cross the vastness between worlds. The Voyagers represent humanity's first step toward becoming a truly spacefaring civilization. Scientists expected to find frozen, lifeless rocks orbiting Jupiter. What they discovered instead changed everything we thought we knew about planetary moons. The cameras revealed something impossible. Oh, one of Jupiter's moons was erupting. Not just one volcano, dozens of them. Some were shooting material hundreds of miles into space. This tiny world turned out to be the most volcanically active place in our entire solar system. The discovery shocked planetary scientists. Though it is much smaller than Earth, it should have cooled down and died billions of years ago. Instead, it's constantly reshaping its own surface with sulfur eruptions that paint it bright yellow and red. The reason for this volcanic fury is gravitational torture. Jupiter's immense gravity squeezes Earth like a stress ball. As the moon orbits, this squeezing and relaxing generates heat inside the rock, enough heat to keep dozens of volcanoes constantly active. Europa's smooth, icy surface hides one of the solar system's most intriguing secrets. Beneath that frozen shell lies something that could change our understanding of where life might exist. An ocean deeper than any on Earth. The Voyager images showed Europa covered in strange cracks and ridges. The ice looked like it had been broken apart and refrozen many times. Scientists realized this pattern could only happen if liquid water was moving underneath. This hidden ocean contains more water than all of Earth's oceans combined. The ice shell acts like a protective blanket, keeping the water liquid despite the freezing conditions in outer space. Tidal heating from Jupiter's gravity provides the energy to maintain this liquid state. The discovery revolutionized our search for extraterrestrial life. We used to think life required a planet in the perfect orbital zone around a star. Europa showed us that life might thrive in hidden oceans throughout the galaxy. Moons could be habitable worlds too. Saturn's rings were supposed to be simple. A few broad bands of ice and rock particles orbiting the planet. The Voyager spacecraft revealed something far more complex and beautiful. A system that forced scientists to completely rethink how planetary rings work. The images showed thousands of individual ringlets instead of just a few major rings. Some rings had strange spokes rotating around the planet like wheel spokes. Others showed braided patterns where material seemed to twist around itself. Even more puzzling were the shepherd moons. These tiny satellites patrol the edges of major rings, keeping the particles confined to narrow bands. Without these cosmic shepherds, the ring material would spread out and disappear into space. The complexity defied explanation. Computer models couldn't reproduce what the cameras were seeing. Saturn's rings revealed that gravitational interactions in space create far more intricate patterns than anyone had imagined. This ring system became a natural laboratory for studying how cosmic forces sculpt matter. Titan presented the biggest surprise of the entire mission. This moon of Saturn shouldn't have any atmosphere at all. Most moons are airless worlds with surfaces exposed to the vacuum of space. Titan broke every rule about what moons could be. The spacecraft discovered an atmosphere thicker than Earth's. Dense orange clouds completely hide the surface from view. The atmospheric pressure at Titan's surface is actually higher than what we experience on Earth. This transformed our understanding of where complex atmospheres could exist. The atmosphere is mostly nitrogen, just like Earth's. But instead of oxygen, it contains methane and other organic compounds. These chemicals create a smoggy haze that gives Titan its distinctive orange color when viewed from space. Most remarkably, Titan has weather systems. Clouds form and move across the sky. Liquid methane falls as rain and collects in lakes and rivers on the surface. This moon operates like a twisted version of Earth, with hydrocarbons playing the role that water plays on our planet. Each planet the Voyagers visited had its own magnetic personality. These invisible force fields, created by electrical currents deep inside the planets, told stories about how these worlds were built and what was happening in their cores. Jupiter's magnetic field turned out to be enormous. It extends millions of miles into space, creating a magnetosphere larger than the Sun itself. This field traps high-energy particles from space, creating deadly radiation belts around the planet. Saturn's magnetic field was perfectly aligned with its rotation axis. This was completely unexpected. Most planets have tilted magnetic fields, but Saturn's field points almost exactly along its spin axis. Scientists still don't fully understand Saturn is so perfectly organized. Magnetic measurements also pointed to hidden activity on some moons. When salty water moves through a magnetic field, it can create electrical signals. Later measurements at Europa and other icy moons provided evidence for hidden oceans beneath the surface. The Voyager instruments detected infrared radiation from each planet they visited. This invisible heat signature revealed where these worlds get their energy and how they distribute it around their surfaces. The results challenged basic assumptions about planetary heat. Jupiter radiates more heat into space than it receives from the Sun. This giant planet has its own internal furnace, still glowing from the heat of its formation billions of years ago. Jupiter is slowly shrinking and converting gravitational energy into heat. Saturn also generates internal heat, but not as much as Jupiter. The difference told scientists about how these gas giants formed and evolved. The amount of internal heat each planet produces depends on its mass and composition. One surprising case was Enceladus, a small moon of Saturn. Despite being tiny and far from the Sun, parts of this moon looked younger and more active than expected. These clues suggested active geology on what should have been a dead, frozen world. The Voyagers analyzed the chemical composition of each planet's atmosphere. These measurements provided a timeline of how the outer solar system formed and evolved over billions of years. Each atmosphere told a different story about planetary development. Jupiter and Saturn have atmospheres dominated by hydrogen and helium. These are the simplest, lightest elements in the universe. The giant planets captured these gases directly from the original solar nebula when the solar system was young. Uranus and Neptune have more complex atmospheric chemistry. They contain higher concentrations of water, methane, and ammonia. These compounds suggest the outer planets formed in a different environment, where heavier materials were more common. The atmospheric data also revealed weather patterns that dwarf anything on Earth. Jupiter's Great Red Spot is a storm larger than our entire planet that has been raging for centuries. Wind speeds on Neptune reach over 1,000 miles per hour, driven by the planet's internal heat source. Each Voyager spacecraft carries humanity's most durable creation. A golden record designed to survive longer than our species, our planet, even our Sun. These aren't ordinary music records. Scientists built these discs from copper and coated them with gold. Gold doesn't rust, corrode, or decay in the vacuum of space. The information is stored as analog grooves, just like old vinyl records, but engineered for cosmic permanence. The records were designed to withstand asteroid impacts, radiation storms, and the freezing cold of deep space. Every detail was planned for maximum durability. The cover plates were made from ultra-pure aluminum to resist cosmic bombardment. These golden discs represent our attempt at immortality. While human civilizations rise and fall, while continents drift and species go extinct, these records will continue sailing through the galaxy. They're designed to remain readable for billions of years, long after Earth itself becomes uninhabitable. How do you explain to aliens how to play a record? You can't use words. You can't use pictures they'd recognize. The scientists found a solution in the universal language of physics. The record covers contain detailed diagrams showing exactly how to operate the playback system. These instructions use hydrogen atoms as a universal measuring stick. Hydrogen is the most common element in the universe, so any advanced civilization would understand it. The diagrams show the correct needle placement, rotation speed, and playing direction. They indicate how long each record should take to play from start to finish. The instructions even specify the proper stylus material and tracking force. The genius lies in using physical constants that remain the same throughout the cosmos. The spin frequency of hydrogen atoms, the speed of light, and basic mathematical relationships work the same way everywhere in the universe. These records speak the only truly universal language we know. The record covers include humanity's most precise address. Not a street number or postal code, but a map showing exactly where Earth sits in the vast galaxy. This map uses the brightest lighthouses in space as reference points. Pulsars are rapidly spinning neutron stars that beam radiation into space like cosmic lighthouses. Each pulsar has its own unique flashing pattern. The record cover shows the directions and pulse rates of 14 pulsars surrounding our solar system. These stellar beacons create a three-dimensional coordinate system. Any civilization finding the record could triangulate Earth's exact position by measuring the current pulse rates and comparing them to the recorded values. The map accounts for how these rates change over time. This cosmic GPS system will work for tens of thousands of years. Even as the pulsars gradually slow down, alien astronomers could calculate backwards to determine when and where the record was created. Our location in space and time is permanently encoded in this stellar map. The records contain carefully chosen images showing what humans look like. Male and female figures stand side by side, displaying the basic anatomy of our species. These silhouettes reveal how we're built and how we move. The images show humans at different life stages, children playing together, adults in various activities, families gathered around meals. These pictures demonstrate our social nature and how we care for our young across generations. Scientists included diagrams of human reproduction and development. They showed DNA structure, cell division, and fetal growth. These biological details explain how human life begins and develops, providing aliens with a complete picture of our reproductive cycle. The selection reveals our physical vulnerability compared to the harsh cosmos around us. We're soft-bodied creatures who need protective atmospheres and narrow temperature ranges. These images honestly portray both our limitations and our remarkable ability to thrive despite our fragility. What does Earth sound like? The records answer this question with a carefully curated collection of natural sounds. Wind rustling through trees, ocean waves crashing on beaches, thunder rolling across storm clouds. Animal voices tell the story of our planet's biodiversity. Whale songs echo from the deep oceans. Birds chirp from forest canopies. Lions roar from African savannas. Each sound represents a different ecosystem and climate zone on our world. The recordings also capture sounds that reveal Earth's geology: volcanoes rumbling, earthquakes shifting rock, glacial ice cracking and sliding. These sounds demonstrate that our planet is geologically active and constantly reshaping itself. This natural soundtrack paints an audio portrait of a world teeming with life. While other planets in our solar system are largely silent, Earth resonates with the sounds of water, weather, and billions of living creatures. Our planet sings with life. The records contain a musical anthology spanning the entire history of human artistic achievement. From ancient folk songs to classical masterpieces to contemporary popular music, each selection represents a different culture and musical tradition. Bach's complex mathematical compositions demonstrate humanity's ability to create beauty through mathematical relationships. Traditional songs from various continents show how different human cultures developed unique musical expressions. These pieces reveal both our diversity and our common creative impulses. The selection includes instruments from around the world, drum beats that mirror human heartbeats, string instruments that extend the range of the human voice, wind instruments that capture the sounds of breathing and air movement. This musical collection serves as humanity's artistic resume. It shows aliens that we don't just survive and reproduce. We create beauty for its own sake. Music reveals something uniquely human about our species, the drive to transform sound into emotional expression. The records contain spoken messages in dozens of human languages. Each greeting offers peaceful intentions and expresses hope for contact with other civilizations. These brief messages represent humanity's desire for cosmic friendship rather than conflict. The greetings range from ancient languages like Latin and Sanskrit to modern tongues spoken by millions today. Each message was carefully chosen to represent different linguistic families and cultural regions. The variety demonstrates humanity's incredible linguistic diversity. Children's voices deliver some of the messages, representing hope for future generations. Their innocent enthusiasm conveys humanity's wonder about the cosmos and genuine excitement about the possibility of meeting alien intelligence. These multilingual greetings serve as humanity's first diplomatic contact attempt. They establish our species as communicative, peaceful, and eager to learn from other civilizations. The messages extend friendship across the vast distances and time scales of space. The records include fundamental mathematical and scientific concepts that showcase human intellectual achievement. These diagrams prove that our species has decoded many secrets of how the universe operates. Mathematical relationships are presented visually. The concept of counting basic arithmetic and geometric principles. These universal concepts should be recognizable to any scientifically advanced civilization. Math provides another form of cosmic common ground. Physics diagrams show our understanding of atoms, molecules, and chemical reactions. The structure of DNA reveals that we've cracked the code of life itself. Solar system diagrams demonstrate our knowledge of planetary motions and celestial mechanics. This scientific showcase proves that humans are more than just another biological species. We're a technological civilization capable of understanding physical laws and applying them to explore space. The records present us as worthy partners for intellectual exchange. A collection of photographs reveals human social life in intimate detail. Families sharing meals, children learning from adults, people working together on common projects. These images show how human society organizes itself. The pictures document human technology and architecture. Cities with their organized layouts, transportation systems that move people across great distances, buildings that demonstrate our ability to reshape environments to meet our needs. Images of human activities reveal our complex social behaviors. Sports competitions showing friendly rivalry. Artists creating works of beauty. Scientists collaborating on research projects. These photos demonstrate cooperation, creativity, and peaceful competition. This visual anthropology lesson introduces human culture to cosmic observers. The photographs show that despite our physical vulnerability, we've created complex societies that allow us to thrive across diverse environments. We're social creatures who accomplish far more together than we could individually. The golden records represent humanity's most ambitious preservation project. These disks must maintain their information for longer than any human artifact has ever survived. The engineering required pushes the boundaries of materials science. The record grooves are carved deeper than normal to resist wear from cosmic dust. The metal composition was chosen to remain stable across temperature extremes that span hundreds of degrees. Even the playback stylus was designed from diamond-hard materials. The storage method itself was revolutionary. Instead of magnetic or electronic storage that degrades over time, the records use purely mechanical information storage. physical grooves that can be read by any civilization that understands basic mechanical principles. These golden discs prove that humans can think far beyond our individual lifespans. We built something designed to communicate across geological time scales, potentially reaching civilizations that won't exist until long after our species has evolved into something unrecognizable. The records are humanity's ultimate message in a bottle, cast into the cosmic ocean. In August 2012, Voyager 1's instruments detected something unprecedented. The solar wind that had been streaming past the spacecraft for decades suddenly stopped. The particle environment around the probe changed completely within days. Scientists realized the spacecraft had crossed the heliopause. That's the boundary where our sun's influence ends and true interstellar space begins. No human-made object had ever traveled this far from home before. This boundary isn't like crossing a border between countries. It's more like a ship leaving a river and entering the ocean. The heliopause marks where solar particles can no longer push against the interstellar medium surrounding our solar system. The crossing proved that human technology could function in completely alien conditions. Voyager 1 became our first ambassador to the space between stars, sending back data from a region that Earth-based telescopes could never study directly. Voyager's magnetic sensors recorded a dramatic shift as it entered interstellar space. The magnetic field strength changed sharply within hours. This wasn't a gradual transition. It was an abrupt switch from one magnetic environment to another. Inside our solar system, the sun's magnetic field dominates everything. This field extends billions of miles in all directions, creating a protective bubble around the planets. Outside this bubble, the galaxy's magnetic field takes control. The galactic magnetic field runs in a different direction from our sun's field. When Voyager crossed the boundary, its instruments detected a sudden change in the magnetic environment. The readings showed that interstellar space has its own organized magnetic structure. This discovery revealed that our solar system exists within a much larger magnetic landscape. The galaxy itself has magnetic highways that guide cosmic particles and influence how matter moves between star systems. Scientists expected interstellar space to be nearly empty. Voyager's particle detectors proved this assumption wrong. The region between star systems contains far more material than anyone predicted. High-energy cosmic rays bombard the spacecraft constantly in this region. These particles have much higher energies than anything found inside our solar system. Some cosmic rays carry more energy than particles created in our most powerful Earth-based accelerators. The particle density in interstellar space is actually hundreds of times higher than in the outer reaches of our solar system. This empty space contains enough material to create noticeable effects on anything traveling through it. These energetic particles tell the story of our galaxy's violent history. They're the debris from exploding stars, colliding galaxies, and other cosmic catastrophes. Interstellar space preserves a record of these ancient events in its particle population. How do you measure the density of space itself? Voyager solved this problem by listening to plasma waves. These are vibrations that travel through the electrically charged gas that fills interstellar space. Plasma waves behave like sound waves, but they travel through ionized gas instead of air. When cosmic events disturb the interstellar medium, they create these waves that propagate across vast distances. Voyager's instruments can detect and analyze these vibrations. By measuring the frequency of these plasma waves, scientists can calculate exactly how much material exists in interstellar space. It's like using sonar to map the ocean floor, but instead mapping the density of space between stars. These wave measurements revealed that interstellar space has a complex structure. Some regions are denser than others, creating a lumpy distribution of matter throughout the galaxy. Our solar system is currently traveling through one of these denser regions. Interstellar space turned out to be much hotter than scientists expected. While the few atoms in this region barely move compared to hot gases, they carry surprisingly high amounts of energy per particle. Temperature in space doesn't work like temperature on Earth. In the near vacuum of interstellar space, individual particles can be extremely energetic even when there are very few of them. It's like having a handful of red-hot coals in a huge empty room. Voyager's instruments measured particle energies equivalent to thousands of degrees. This high-energy environment exists because interstellar space is constantly being stirred up by shock waves from exploding stars and other cosmic violence. The temperature difference between our solar system and interstellar space creates a natural boundary. Hot interstellar gas pushes against our sun's cooler solar wind, forming the heliopause where these two environments meet and struggle for dominance. The boundary between our solar system and interstellar space isn't a simple wall. Voyager discovered a complex system of shock waves where these two environments collide. It's like cosmic weather happening on an unimaginable scale. Solar wind rushes outward from our sun at tremendous speeds. When this fast-moving stream of particles hits the interstellar medium, it creates shock waves similar to a jet aircraft, breaking the sound barrier. These shock waves compress and heat both the solar wind and interstellar materials. The collision zone stretches across millions of miles, creating a turbulent boundary region where the two environments mix and fight for control. This shock wave system protects our solar system from some galactic dangers. It deflects high-energy cosmic rays and filters out harmful radiation that could otherwise penetrate deeper into our planetary neighborhood. Interstellar space contains vast clouds of neutral hydrogen atoms. These atoms don't carry electric charge, so they can drift freely through the galaxy without being affected by magnetic fields. Voyager became our first direct probe of this invisible cosmic gas. Neutral hydrogen represents the raw material from which new stars form. These atoms eventually clump together under gravity, heat up, and ignite nuclear fusion. By measuring hydrogen distribution, scientists can predict where future star formation might occur. Our solar system is currently passing through what astronomers call the local interstellar cloud. This hydrogen-rich region extends across dozens of light years and affects the space environment around our planets. The hydrogen measurements revealed that our galaxy has a complex structure of gas clouds, empty regions, and dense filaments. These discoveries help scientists understand how matter moves through the galaxy and how stellar neighborhoods evolve over cosmic time. Interstellar space buzzes with high-energy particles called cosmic rays. These particles travel at nearly the speed of light and carry enormous amounts of energy. Our solar system's magnetic field normally deflects most of them away from Earth. Voyager's instruments detected cosmic ray intensities much higher than anything measured inside our solar system. Some of these particles pack enough energy to damage living tissue or disrupt electronic equipment. They represent one of the major hazards for future interstellar travel. The cosmic rays come from all directions, suggesting they've been scattered and accelerated by magnetic fields throughout the galaxy. Supernova explosions, black holes, and other violent cosmic events continuously pump new high-energy particles into this galactic radiation environment. These measurements revealed that our sun's magnetic bubble provides crucial protection for life on Earth. Without this natural shield, our planet would be constantly bombarded by radiation levels that could sterilize the surface. Scientists expected interstellar magnetic fields to be incredibly weak. Voyager's magnetometer revealed fields several times stronger than predicted. This discovery forced astronomers to reconsider how magnetic forces shape our galaxy. The stronger magnetic field helps explain how cosmic rays get accelerated to such high energies. Magnetic fields can act like cosmic particle accelerators. whipping charged particles to tremendous speeds as they spiral along field lines. Interstellar magnetic fields also play a crucial role in star formation. They can compress gas clouds or prevent them from collapsing under gravity. The field strength measured by Voyager suggests magnetic forces have more influence on galactic evolution than previously thought. This magnetic discovery connects to larger questions about how galaxies form and evolve. Magnetic fields might help determine which regions of a galaxy can form new stars and which remain empty of stellar activity. The edge of our solar system isn't a sharp boundary. Voyager discovered a complex transition zone where solar and interstellar environments gradually blend together. This boundary layer extends across millions of miles of space. The transition happens in stages. First, solar wind particles slow down as they encounter interstellar resistance. Then magnetic fields begin to shift direction. Finally, the particle environment completely changes as interstellar cosmic rays take over. This layered boundary structure reveals that cosmic environments don't have sharp edges. Instead, they create complex transition zones where different physical conditions gradually give way to each other. Understanding this boundary architecture helps scientists predict what future interstellar missions might encounter. The transition zone acts like a cosmic buffer that slowly acclimates spacecraft to the hostile environment of true interstellar space. What happens when you travel to the emptiest place imaginable? You discover it's not empty at all. Voyager's particle detectors revealed that interstellar space contains far more material than anyone expected. Scientists used to think the space between stars was essentially a vacuum. They imagined vast regions of pure nothingness stretching between stellar systems. The reality turned out to be completely different. Every cubic inch of interstellar space contains thousands of atoms and molecules. Hydrogen dominates the mix, but helium, carbon, and heavier elements float freely through this cosmic medium. Dust grains smaller than smoke particles drift along with the gas. This discovery revolutionized our understanding of galactic structure. Interstellar space isn't empty. It's a thin but vast reservoir of matter that connects all the stars in our galaxy. The space between stars actively participates in galactic evolution. Our entire solar system is currently traveling through a cosmic cloud. This cloud stretches across dozens of light years and affects the space environment around all our planets. Voyager became our first direct probe of this galactic neighborhood. Astronomers call this region the local interstellar cloud. It's a relatively dense patch of gas and dust that formed from ancient stellar explosions. Our solar system entered this cloud thousands of years ago and will eventually exit into a different region. The cloud has its own temperature, density, and chemical composition. It's slightly warmer and denser than average interstellar space. These conditions affect how cosmic rays reach our solar system and influence the pressure on our sun's protective magnetic bubble. This local environment changes over cosmic time as our solar system moves through the galaxy. We're essentially sailing through an ocean of interstellar clouds, each with different properties that gradually alter our cosmic neighborhood. Magnetic fields thread through the entire galaxy like invisible highways. These fields guide the motion of charged particles across vast distances and help organize the structure of interstellar space. Voyager's magnetometer revealed how powerful these galactic magnetic forces really are. The galactic magnetic field isn't random. It follows the spiral structure of our galaxy's arms. Charged particles get funneled along these magnetic highways, creating streams of cosmic traffic flowing between star systems. These magnetic fields also act like cosmic construction workers. They help squeeze gas clouds until they collapse to form new stars. They channel material from dying stars into the interstellar medium. Without these organizing forces, our galaxy would be a chaotic mess. The magnetic measurements show that our galaxy operates like a giant machine with magnetic gears and pulleys moving matter around on cosmic scales. These invisible forces shape everything from star formation to the paths that cosmic rays follow through space. Where do the most energetic particles in the galaxy come from? Voyager's cosmic ray detectors solved this mystery by measuring particle energies in interstellar space. The answer reveals a galaxy shaped by spectacular violence. Cosmic rays are particles accelerated to incredible speeds by some of the most powerful events in the universe. Exploding stars, colliding galaxies, and supermassive black holes all contribute to this high-energy particle population. Some cosmic rays carry more energy than particles in our most powerful Earth-based accelerators. These particles have been racing through space for millions of years, bouncing off magnetic fields and gaining energy with each collision. The energy distribution of these particles creates a detailed fingerprint of galactic violence. By analyzing cosmic ray energies, scientists can identify which types of cosmic catastrophes are most common and how they've shaped our galaxy's evolution over billions of years. Why do distant stars appear dimmer and redder than they should? The answer lies in microscopic dust grains floating throughout interstellar space. These tiny particles intercept starlight and scatter it in all directions. Interstellar dust consists of particles smaller than cigarette smoke. Most grains are made of carbon or silicon compounds with ice coatings. These particles form in the atmospheres of dying stars and get blown into space by stellar winds. The dust doesn't just block starlight, it transforms it. Blue light gets scattered more than red light, making distant stars appear redder than they actually are. This reddening effect confused astronomers for decades before they understood its cause. Dust grains also serve as cosmic construction materials. They provide surfaces where atoms can stick together and form molecules. Without interstellar dust, the complex chemistry needed for star and planet formation would be nearly impossible. Can you hear sounds in the vacuum of space? Not exactly, but Voyager detected something similar. Waves that travel through the electrically charged gas filling interstellar space. These plasma waves carry information across the galaxy. Plasma waves behave like sound waves, but they travel through ionized gas instead of air. When cosmic events disturb the interstellar medium, they create waves that can propagate for thousands of light years before fading away. Different frequencies reveal different aspects of interstellar structure. Low-frequency waves probe large-scale galactic features. High-frequency waves respond to local disturbances like shock waves from exploding stars. By listening to these plasma vibrations, Voyager essentially gave scientists ears in interstellar space. These wave measurements reveal the density, temperature, and magnetic field strength of regions too distant for any other type of observation. Interstellar space has its own weather system with hot and cold regions mixing together in complex patterns. Voyager's temperature measurements revealed that the space between stars operates more like an active atmosphere than a static void. Different regions of interstellar space can vary in temperature by thousands of degrees. Hot zones form around exploding stars and stellar nurseries. Cold regions develop in the shadows of dense dust clouds where starlight cannot penetrate. These temperature differences drive interstellar weather patterns. Hot gas expands and pushes against cooler regions. Cold gas contracts and flows toward areas of lower pressure. The result is a constantly churning cosmic atmosphere. Temperature variations also control where new stars can form. Gas clouds need to cool down before gravity can squeeze them into star-forming regions. The thermal structure of interstellar space determines which parts of the galaxy remain active and which stay dormant. Every star that ever lived and died left chemical fingerprints in interstellar space. Voyager's instruments detected these elemental signatures, revealing the complete life cycle history of our galactic neighborhood. Heavy elements like carbon, oxygen, and iron didn't exist when the universe began. They were forged inside massive stars and scattered into space when those stars exploded. Each generation of stars added new chemical complexity to the interstellar medium. The chemical composition varies from region to region, telling stories about local stellar history. Areas near recent supernovas are enriched with freshly made heavy elements. Regions far from star formation remain mostly hydrogen and helium. This chemical archaeology allows scientists to trace how our galaxy evolved from a simple hydrogen cloud into a complex system capable of forming rocky planets and organic molecules. The space between stars preserves a detailed record of cosmic chemical evolution. Why doesn't interstellar space separate into layers like oil and water? The answer is turbulence. Chaotic flows that constantly stir and mix the galactic medium. Voyager revealed that interstellar space behaves more like a stormy ocean than a calm lake. Exploding stars inject enormous amounts of energy into interstellar space. This energy creates shock waves that travel outward for thousands of light years, stirring up everything in their path. Turbulent mixing prevents the galaxy from stratifying into simple layers. Heavy elements get distributed throughout the galactic disk instead of settling toward the center. This mixing process is essential for spreading the materials needed for planet formation. The turbulent structure also affects star formation rates. In calm regions, gas can collapse smoothly to form stars. In turbulent zones, the chaotic motions can either enhance star formation by compressing gas clouds or prevent it by dispersing the material. How do you cross from one cosmic neighborhood to another? Voyager discovered that interstellar space is divided into distinct regions separated by invisible boundary layers. These boundaries mark transitions between areas with different physical properties. Each interstellar cloud has its own chemical composition, temperature, and density. When these clouds interact, they create boundary zones where the properties gradually change from one region to another. Some boundaries are sharp transition zones where conditions change dramatically over short distances. Others create gradual transition regions that can stretch across multiple light years. These boundary layers control how matter and energy flow through the galaxy. They can act as barriers that contain material within local regions, or as conduits that allow exchange between different cosmic neighborhoods. Understanding these boundaries helps scientists map the large-scale structure of our galactic environment. What if everything we knew about empty space was wrong? Voyager's instruments revealed that interstellar space contains far more material than anyone expected. The region between star systems isn't a cosmic vacuum at all. Scientists used to think interstellar space was nearly empty. Just a few lonely atoms floating in an infinite void. Voyager's particle detectors shattered this assumption completely. The empty space between stars buzzes with activity. Every cubic inch of interstellar space contains thousands of atoms and molecules. That might not sound like much, but it's hundreds of times denser than the space near Pluto. This invisible material creates drag on anything moving through it. The discovery revealed that our galaxy has a complex material landscape. Dense clouds, thin regions, and streams of flowing gas create an intricate three-dimensional structure throughout the space between stars. Our entire solar system is currently traveling through a massive cloud of gas and dust. This cloud stretches across dozens of light years and affects the space environment around all our planets. Scientists call it the local interstellar cloud. This cloud isn't like the fluffy white clouds you see in Earth's sky. It's an incredibly thin collection of atoms and particles that would count as a perfect vacuum in any Earth laboratory. Yet by interstellar standards, it represents a relatively dense region. The cloud contains mostly hydrogen atoms along with small amounts of helium and heavier elements. These atoms came from stars that exploded billions of years ago, seeding space with the building blocks for future worlds. Our solar system has been moving through this cloud for tens of thousands of years. The cloud's properties affect how cosmic radiation reaches Earth and influences the boundary where our solar system meets interstellar space. Interstellar space has invisible highways made of magnetic fields. These field lines stretch across the entire galaxy, creating a vast transportation network for charged particles. Voyager became our first direct probe of this cosmic infrastructure. Magnetic field lines in space work like train tracks. Charged particles get trapped and forced to follow these invisible pathways. The particles spiral along the field lines, unable to move perpendicular to the magnetic direction. This galactic magnetic field is much stronger than scientists predicted. The field strength measured by Voyager suggests that magnetic forces play a major role in how our galaxy is organized and how it evolves over time. The magnetic highways help explain how cosmic rays get accelerated to such incredible energies. Particles can surf along these field lines for thousands of years, gaining speed from magnetic interactions until they become cosmic missiles racing through space. Interstellar space rains high-energy particles called cosmic rays. These particles carry more energy than anything humans can create in our most powerful laboratories. Voyagers detect and measure this cosmic particle storm directly. Cosmic rays are the debris from cosmic catastrophes. When massive stars explode as supernovas, they blast particles into space at nearly the speed of light. Black holes and colliding galaxies also contribute to this high-energy particle population. The energy levels are staggering. Some cosmic ray particles pack enough punch to damage living tissue or destroy electronic circuits. They represent one of the biggest challenges for future human missions to other star systems. These particles tell the story of our galaxy's violent history. Each cosmic ray carries information about the explosive event that created it, providing Voyager with a direct sample of galactic archaeology. Microscopic dust grains float throughout interstellar space. These particles are smaller than cigarette smoke, but they play a huge role in how we see the universe. Voyager detected these tiny cosmic dust specks directly for the first time. Interstellar dust absorbs and scatters starlight as it travels across the galaxy. This cosmic smog makes distant stars appear dimmer and redder than they actually are. It's like trying to see through fog, but on a galactic scale. The dust grains form in the atmospheres of dying stars. As these stars puff off their outer layers, the material cools and condenses into tiny solid particles. Stellar winds then blow these grains into interstellar space. This cosmic dust eventually becomes the raw material for new worlds. The grains stick together over millions of years, gradually building up into asteroids, comets, and planets. Our own Earth formed from dust like this long ago. Interstellar space rings with invisible vibrations called plasma waves. These waves travel through the electrically charged gas that fills the region between stars. Voyager's instruments can hear these cosmic sound waves directly. Plasma waves work like sound waves, but instead of traveling through air, they move through ionized gas. When something disturbs the interstellar medium, it creates ripples that propagate across vast distances at specific frequencies. By analyzing these wave frequencies, scientists can measure the exact density of interstellar space. It's like using sonar to map the ocean floor, but instead mapping the invisible material between stars. The waves also carry information about distant cosmic events. Shock waves from exploding stars, colliding gas clouds, and other violent phenomena create distinctive wave patterns that Voyager can detect and analyze. Interstellar space exhibits a strange temperature paradox. The few atoms in this region barely move compared to hot gases on Earth, yet they carry surprisingly high amounts of energy per particle. This contradiction puzzled scientists for years. Temperature in space doesn't work like temperature in your living room. In the near vacuum of interstellar space, you can have extremely energetic particles even when there are very few of them around. Voyager measured particle energies equivalent to thousands of degrees. This happens because interstellar space gets constantly stirred up by shock waves from exploding stars and other cosmic violence. These events heat the sparse gas to incredible temperatures. The temperature structure reveals that interstellar space has multiple layers with different energy levels. Hot regions mix with cooler zones, creating a complex thermal landscape that varies throughout the galaxy. The chemical composition of interstellar space tells the story of stellar generations. Voyager's instruments analyzed the mix of elements floating between the stars, revealing how our galaxy has evolved over billions of years. Interstellar space contains a surprisingly rich chemical inventory. Hydrogen and helium dominate, but heavier elements like carbon, oxygen, and iron are also present. These heavy elements didn't exist when the universe was young. Every heavy element in interstellar space was forged inside a star and then expelled when that star died. The chemical ratios measured by Voyager reveal how many generations of stars have lived, died, and enriched the galaxy with their remains. This cosmic recycling process continues today. New stars form from interstellar gas enriched by previous stellar generations, creating an ongoing cycle that gradually increases the heavy element content of the galaxy. Interstellar space isn't calm and peaceful. Voyager discovered that the interstellar medium churns with turbulent motions that mix materials across vast regions. It's like cosmic weather happening on an unimaginable scale. Turbulence in interstellar space works similarly to atmospheric turbulence on Earth, but the scales are mind-boggling. Swirling motions stretch across dozens of light years, driven by energy from exploding stars and colliding gas clouds. This cosmic turbulence helps distribute heavy elements throughout the galaxy. Without this mixing process, the products of stellar nucleosynthesis would remain localized, preventing the formation of planets and life in other regions. The turbulent motions also play a crucial role in star formation. They can compress gas clouds to trigger gravitational collapse or disrupt them to prevent star birth, determining which regions of the galaxy remain active. Interstellar space isn't uniform. Voyager revealed distinct regions with different properties, separated by relatively sharp boundaries. These cosmic neighborhoods have their own unique characteristics and behaviors. Our local interstellar cloud represents just one neighborhood in a complex galactic community. Adjacent regions have different densities, temperatures, and chemical compositions. The boundaries between these regions can be surprisingly abrupt. These boundary zones act like cosmic weather fronts where different interstellar environments meet and interact. Pressure differences between regions drive flows of material from one cosmic neighborhood to another. Understanding this neighborhood structure helps scientists predict what future interstellar missions might encounter as our solar system continues its journey through the galaxy. We're currently residents of one specific cosmic community, but that will change over cosmic time. Every year, Voyager's power supply gets a little weaker. The spacecraft runs on nuclear batteries that generate electricity through radioactive decay. This process naturally slows down over time, and there's no way to recharge the batteries in deep space. The power source uses plutonium-238, a radioactive material that converts heat directly into electricity. As the plutonium atoms decay, they produce less heat each year. The power output drops a little each year. Mission controllers face impossible choices as the power dwindles. They must decide which scientific instruments to keep running and which to shut down forever. Each decision means losing valuable data from humanity's most distant outpost. The nuclear batteries were designed to last far longer than the original mission required. Their remarkable longevity has allowed the Voyagers to keep transmitting decades beyond their planned lifespans. But physics ensures this power source will eventually fail completely. How do you aim a radio antenna across billions of miles of space? Voyager must point its dish antenna toward Earth with incredible precision while traveling through the cosmic void. Getting the aim wrong means losing contact forever. From Voyager's distance, Earth appears as an incredibly tiny target. The spacecraft's antenna must maintain pointing accuracy better than aiming a laser pointer at a coin from across an entire city. Any slight drift in orientation breaks the communication link. The spacecraft uses gyroscopes and small thruster jets to maintain its orientation. These systems automatically adjust the spacecraft's position to keep the antenna pointed toward Earth as both objects move through space. This pointing challenge becomes harder every day as Voyager travels farther away. The margin for error gets smaller while the spacecraft's aging attitude control system becomes less reliable with each passing year. By the time Voyager's radio signals reach Earth, they're almost impossibly weak. The signal power that arrives at our planet is measured in tiny fractions of a watt. It's like trying to detect the light from a single candle flame on the moon. Radio signals obey the inverse square law. They get weaker as distance increases. Double the distance, and the signal becomes 4 times fainter. Voyager's tremendous distance makes its signals billions of times weaker than when the mission began. The spacecraft transmits with only a few watts of power, about the same as a small light bulb. After traveling across the solar system, this already weak signal becomes almost undetectable by the time it reaches Earth's vicinity. These ghostly weak signals carry humanity's most distant scientific data. Every bit of information that reaches us represents a triumph over the vast emptiness of space and the fundamental laws of physics that work against long-distance communication. NASA operates the most sensitive radio telescopes on Earth specifically to hear Voyager's faint signals. These massive dish antennas can detect radio waves weaker than any cell phone signal ever measured. They represent humanity's most advanced listening posts. The Deep Space Network consists of 3 giant antenna complexes spread around the world. As Earth rotates, at least one station always faces toward Voyager's location in space. This ensures continuous communication capability. Each antenna dish spans over 200 feet in diameter. These enormous collecting surfaces gather radio waves from space and focus them onto sensitive receivers. The larger the dish, the weaker the signals it can detect. The receivers operate at temperatures colder than liquid nitrogen to reduce electronic noise. Any heat in the electronics would create random signals that could overwhelm Voyager's faint transmissions. How do you send scientific data when your communication channel is slower than dial-up internet? Voyager solves this problem through sophisticated data compression that squeezes maximum information into minimum transmission time. The spacecraft can only transmit a few bits of data per second. This rate is thousands of times slower than even the most basic internet connection. Every bit of transmission time is precious and must be used efficiently. Mission scientists developed compression algorithms specifically for Voyager's data types. Images get compressed by focusing on the most scientifically important details while discarding redundant information. The spacecraft also prioritizes which data to send first. The most critical scientific measurements get transmitted immediately, while less urgent data waits in electronic storage for later transmission opportunities. What happens when cosmic noise corrupts the data during transmission? Voyager uses error correction codes that can rebuild perfect information from damaged signals. These mathematical techniques ensure that scientific data arrives intact despite the hostile space environment. Radio signals can get corrupted by cosmic radiation, solar storms, or interference from Earth-based sources. Without error correction, much of Voyager's data would arrive garbled and useless. The spacecraft adds extra mathematical information to each data packet. This redundant coding allows Earth-based computers to detect and fix transmission errors automatically. The error correction system works so well that scientists can receive perfect copies of Voyager's data, even when the original signal is partially corrupted during its journey through space. Mission controllers face a constant battle to stretch Voyager's remaining power as far as possible. They've developed ingenious strategies for keeping the most important systems running while shutting down everything else. Non-essential systems get turned off permanently to save power. Scientific instruments that have completed their primary objectives get shut down to preserve electricity for more critical functions. The spacecraft's computer systems run on minimal power by operating more slowly than desktop computers from decades ago. Every electronic component was designed for maximum efficiency rather than speed. Heaters that keep instruments warm get turned off in sequence as power becomes scarce. This gradual cooling process prioritizes the most critical systems, while allowing less important components to freeze. When mission controllers send a command to Voyager, they must wait almost 2 full days to learn whether it worked. Radio signals travel at the speed of light, but even light takes many hours to cross the vast distance to the spacecraft. This communication delay makes real-time spacecraft control completely impossible. Controllers must plan every command sequence carefully, and knowing they can't quickly fix problems if something goes wrong. The spacecraft operates mostly on autopilot, following programmed instructions for days or weeks at a time. It must handle emergencies and routine operations without waiting for commands from Earth. This forced autonomy has made Voyager one of the most independent machines humans have ever built. The spacecraft makes critical decisions about its own survival while Earth remains impossibly far away. Can a spacecraft think for itself? Voyager operates with a primitive form of artificial intelligence that allows it to respond to emergencies without human intervention. This autonomy becomes more critical as communication delays increase. The spacecraft monitors its own health constantly. If critical systems overheat, lose power, or malfunction, onboard computers automatically take corrective action without waiting for instructions from Earth. Voyager can switch to backup systems when primary equipment fails. It can adjust its orientation to keep its antenna aimed toward Earth. These survival reflexes operate faster than ground controllers could possibly respond. This autonomous intelligence represents one of humanity's first successful attempts at creating machines that can survive independently in the most hostile environments imaginable. Why do the Voyagers keep working decades after their expected failure date? The answer lies in redundant backup systems that take over when primary equipment fails. Every critical component has at least one spare waiting in reserve. The spacecraft carry duplicate computers, radio transmitters, and scientific instruments. When one system fails, its backup automatically activates to continue the mission without interruption. Some backup systems have lasted longer than the original primary equipment. Components designed as emergency spares have operated continuously for years, proving their reliability in the harsh environment of deep space. This redundancy philosophy has allowed the Voyager missions to survive countless equipment failures that would have ended less robust spacecraft. The backups keep backing up the backups, creating layers of reliability that refuse to surrender to the inevitable decay of aging electronics. Once their power dies, the Voyager spacecraft will enter a completely different phase of existence. They'll become objects in perpetual motion, sailing through space without engines, fuel, or any external energy source. Newton's laws of motion ensure they'll continue moving unless something stops them. In the vacuum of space, there's nothing to slow the spacecraft down. No air resistance, no friction. No gravity strong enough to pull them back toward our solar system. They'll coast on pure momentum for billions of years. This eternal journey operates on the most fundamental principle of physics. Objects in motion stay in motion unless something stops them. The vast emptiness between stars provides the perfect environment for this cosmic coasting. The spacecraft have already reached escape velocity from our solar system. They're now free-flying objects of the galaxy itself, following trajectories that will carry them past other star systems over cosmic time scales that dwarf human history. Where will Voyager travel during humanity's future? Computer simulations predict both spacecraft will eventually pass near other star systems. These encounters won't happen for tens of thousands of years, long after human civilization has transformed beyond recognition. Voyager 1 is heading toward the constellation Ophiuchus. In about 40,000 years, it will pass within a few light years of a red dwarf star called Gliese 445. This will be humanity's first robotic visit to another stellar neighborhood. Voyager 2 follows a different path through the galaxy. It will encounter different stars on its own schedule, creating two separate threads of human exploration stretching across interstellar space. These future encounters represent humanity's first attempt at true interstellar exploration. While we can't control or communicate with the spacecraft during these distant meetings, they'll carry our presence into alien solar systems where no Earth-based signal could ever reach. What happens to humanity's message when the spacecraft finally go silent? The golden records will continue their mission long after the electronics die. These metal time capsules were designed to survive conditions that would destroy any Earth-based artifact. The records can withstand cosmic radiation levels that would sterilize entire planets. They'll survive temperature extremes from near absolute zero to the heat of stellar radiation. Micrometeorite impacts might scratch the surface but won't destroy the encoded information. While human monuments crumble and civilizations rise and fall, these golden discs will preserve a snapshot of our species at the moment we first reached for the stars. They represent humanity's longest-lasting cultural achievement. The records will remain readable for billions of years, potentially outlasting our sun itself. They're designed to tell our story to cosmic archaeologists who won't encounter them until Earth's biosphere has completely transformed or disappeared. Every day, Voyager 1 sets a new record as the most distant human-made object. This record will likely stand for a very long time, since no current or planned mission is expected to travel farther from Earth. The spacecraft has become humanity's permanent deep space champion. Future interstellar missions might travel faster, but they'll start from a solar system that Voyager has already left behind. Unless humanity builds spacecraft capable of incredible speeds, nothing will catch up to these early pioneers. The distance record represents more than just numbers. It symbolizes humanity's reach beyond our planetary cradle. Voyager proves that our species can create technology that transcends the boundaries of worlds and solar systems. This achievement becomes more remarkable with each passing year as the spacecraft continue their relentless journey into deeper space, extending humanity's physical presence farther into the cosmic frontier. What scientific impact do two aging spacecraft have on human knowledge? The Voyager discoveries fundamentally changed our understanding of planetary science, space physics, and the structure of our local cosmic environment. Every major astronomy textbook contains information that Voyager provided. The missions revealed that our solar system is far more complex and dynamic than anyone imagined. Active volcanoes on distant moons, underground oceans that might harbor life, and magnetic fields that shape entire planetary systems, all discovered by these robotic explorers. The boundary crossing into interstellar space created an entirely new field of study. Scientists now understand how our solar system interacts with the galactic environment, knowledge that's impossible to gain from Earth-based observations alone. These discoveries will influence space science for generations to come. Future missions to the outer solar system and beyond will build on the foundation that Voyager established through direct exploration of previously unknown territories. Can human technology survive the journey between stars? Voyager answered this question definitively. The spacecraft demonstrated that properly designed machines can function reliably across interstellar distances and time scales. The missions proved that nuclear power sources can operate for decades in deep space. They showed that autonomous navigation systems can maintain course without ground control. They demonstrated that sensitive scientific instruments can continue working in the harshest environments imaginable. This technological validation provides the foundation for future interstellar missions. Engineers now know which designs work and which fail when pushed to cosmic extremes. The reliability demonstration extends beyond just hardware. It proved that human mission planning and engineering can anticipate challenges across unprecedented distances and time scales, giving confidence for even more ambitious future missions. How do you measure the inspiration that two spacecraft generated? The Voyager missions captured public imagination in ways that continue influencing space exploration decades later. They proved that robotic missions could be as compelling as human spaceflight. The iconic images of Jupiter's swirling clouds, Saturn's delicate rings, and strange moons with active geology brought the outer solar system into human consciousness. These discoveries made distant worlds feel real and accessible to ordinary people. The missions inspired countless students to pursue careers in science and engineering. They demonstrated that patient, careful exploration could reveal wonders that exceed science fiction imagination. This inspirational legacy continues, growing as new generations discover Voyager's achievements and realize that humans can build machines capable of crossing the ultimate frontier between star systems. What comes after Voyager? Space agencies worldwide are developing new interstellar missions that will build on these pioneering achievements. The Voyagers blazed a trail that future spacecraft will follow with improved technology and expanded capabilities. Proposed interstellar probe missions would travel much faster than Voyager, reaching nearby star systems within decades instead of millennia. They would carry modern instruments capable of detailed analysis of alien worlds. Some concepts include swarms of tiny spacecraft that could explore multiple star systems simultaneously. Others propose nuclear-powered probes that could operate for centuries while maintaining communication with Earth. The success of Voyager's interstellar crossing provided proof that such ambitious missions are technically feasible, encouraging space agencies to invest in developing the next generation of interstellar explorers. When will humanity lose contact with the Voyagers forever? The spacecraft are approaching the limits of their communication ability as power levels drop and distances increase. This silence will mark the end of their active mission phase. Power levels will drop below the threshold needed for radio transmission sometime in the mid-2020s. The exact date depends on how efficiently mission controllers can manage the remaining energy budget. After communications end, the spacecraft will become truly independent Voyagers. They'll continue their journeys without any connection to their home planet, following the trajectories that human planners designed decades earlier. This approaching silence adds poignancy to every remaining data transmission, knowing that each signal brings us closer to the moment when these distant ambassadors will disappear into cosmic anonymity. What do the Voyager spacecraft represent in the largest possible context? They're more than just machines. They're Earth's first permanent ambassadors to the galaxy. They carry not just human artifacts, but samples and sounds representing our entire planet's biosphere. The spacecraft bear golden records containing sounds of Earth's winds, waters, and wildlife. They carry mathematical principles, scientific knowledge, and artistic achievements that represent the pinnacle of terrestrial intelligence. In a galaxy containing billions of star systems, these tiny machines represent the first successful attempt by any Earth species to send permanent representatives beyond our solar system. The Voyagers have transformed humanity from a purely planetary species into a species with its first artifacts in interstellar space, proving that life from our small blue world can create technology capable of crossing the vast ocean of space that separates the stars.